Hello friends. So till the previous video we have seen the calculation of this first non-dominant pole or pole contributed by this node Y. Okay, and before that we have seen the pole contributed by this capacitance CL. Now it's the time to calculate the zero due to this node Y. Okay, so is there any possibility of zero due to C by cap? We will see. So first we will see what is the condition or what are the conditions for zero calculation. Generally, what we make the H of S should be zero, where V out by V in should be zero, because we are calculating the zero. I mentioned in the big the zero. So everything should be zero. I mean to say transfer function should be zero, output should be zero, and for making that output to zero, there are possibilities. Two current paths from input to output, and at least one path should have a reactive element. Well, I think these things I told many times in detail, so I will not cover this thing again. But yes, you should understand there should be two paths from input to output, and if these two paths has some impedance, like the impedances are out of phase, or we can say one is the negative of other, then we can say there is a possibility of zero, and zero will be there. And the other thing is that sum of two voltages should result your V out. Let's say this. So this V out is nothing but these two Z1 and Z2. The connection of these two impedances from V out to ground is there, and V out is nothing but a sum of these two voltages V1 and V2. And if at least one out of Z1 Z2 is the reactive, then you can say your output can be zero for particular amount of current flowing across it. Okay, so these are two ways. So, what we will see, I think I will not cover these things now. Just I mentioned here the conditions for zero calculation. You can see this thing or you can watch this thing in the previous video. Now we will exactly see what is happening for this 5 transistor OTS structure in terms of zero calculation. Okay. So, what you will see here, so there are two paths uh, to the output. One path is this and other path is this. Okay. So, what is happening, I don't know. But yeah, this is the one path I2 and I4 this path. Overall, what will I say? The I, which is nothing but making my output to zero for V out to zero. What I will do, I should be zero. Okay, and for that we can see I2 plus I4 should be zero. So this is the this is a very basic the condition for the zero calculation. So how I4 is coming? I4 is coming due to this mirroring of the current from this M3 that I should mention here. This is my M3. So this is our M3. This is our M4. So the sum of two currents I2 and I4 should be zero. We will get the zero. Okay, no problem. So how will we get this? We have to calculate and see it here. So as we are calculating zero, we will not short our input. Input will be available here, Cy, and this node is Y. I want to make my output to 0, and for that I want to make this I to be 0. Okay, so we'll simply calculate it. What is happening here? Okay, so this is a Y voltage, a node voltage, this is Y. So, okay, so what should be the current in this branch? And what should be the current in this branch? And what should be the current in this branch? Okay, we will see all the currents and then we will exactly make the currents to be zero. Okay, so let I should mention here, this is my I3 and this is I1. Okay, and here is our I2, this is my I4. Okay, so first thing that you will see, my I4 is equal to I3, which is nothing but a mirroring. Okay, due to mirroring. And what is the other current? Other current is what? This is the current that is flowing this way. There is one current from what I should say. I should say I of C Y. It is what? Vy times Cy S. This is the one current. Okay. So what is exactly the I1? I1 equal to minus of I3 plus ICY. I think there is no confusion in that. So it is I3 plus by cys. This is the I1. Okay, so this thing we already know that this when this I1 will split here at a node X, nearly zero current will flow to this and all current will go here. What I can say, I2 is nothing but minus of I1. Okay, so simply we'll say that what is my I. Okay, so first I should write I2. I2 is nothing but minus of I1, which is nothing but plus of I3 plus V by C by S. Okay, so this is the amount of current is coming out. Now, what is I? I is nothing but minus of I2 plus I4. Okay, so it is nothing but we have to make this zero. So what is I2? I2 we have seen. So simply I should say I have to make I2 plus I4 equal to 0. This also mean I have to make I2 because I4 is equal to I3. So I have to make I2 plus I3 0, and I2 I know I3 plus okay, I2, this is sorry, this is the expression for I2. So I3 plus Vy Cys equal to 0. So what is here? 2I3 plus Cy Vys equal to 0. So what we are getting here? Okay, so this is the equation we got. 2I3 plus Cys times Vy equal to 0. Now I have to find the relation between I3 and Cy. Sorry, Vy. So that relation is very simple. What will can be the relation? We can directly find what is my I3. So we can directly see this. This is grounded, and this node is my Vy is also same node. So the gate voltage is Vy. So if I want to write the equation for IDS of 3, which is equal to I3 that I am considering here. So what is this IDS? IDS I always mention, always write a current from drain to source, which is equal to GM of that particular device times VGS of that particular device plus some order of GDS and other terms are also there. So I will ignore for time being, but you can also write it. No body effect term because BBS is 0. Okay, so what it can be there? GM3 BY plus GDS3 BY. Okay, so what it can be written is GM3 plus GDS3 BY, and we also know one thing. I should change the color. We also know one thing that here I should write GM3 is much greater than this GDS3. Okay, so what it can be? IDS3, which is also I3, is equal to GM3 By. Okay, so what we can put? We can put the value of I3 in this equation. So what 2 GM3 By plus CYS By equal to 0. So if we take the By common, what it will be? 2 GM3 plus Cys equal to 0. So what is S coming from here? We are getting S equal to minus 2gm3 by Cy. So what is the magnitude of this omega? That is not P, it is Z. So it is omega Z. Okay, so this is the omega G, the magnitude 2gm3 by Cy. Okay, so this was our target to calculate. So we have seen, we made two currents equal to like sum of the two currents equal to 0 because this is the I only. and this is the only way of calculation of 0. So what we got here. So what we have seen, omega g I got 2 gm 3 by cy. And what to speak of omega p2? Omega p2 by gm 3 by cy. Okay, so what I can say, omega g equal to 2 times of omega p2. So they are like always at the equidistance, so we cannot make any separation between omega g and omega p2, because one is twice of other, so they are correlated, I can say. One thing that we should keep here, the negative sign indicate that left hand side 0, which is good for stability. Okay, it is good for stability. So this thing we have seen. Now we'll see the other the pole which is contributed by, this is the omega p3 contributed by cx, which is nothing but rx cx, and rx we can calculate here. Okay, so before calculating this pole, I will talk little more about this zero, the interesting fact that I told here. So what is interesting here? So okay, so as we are calculating the poles and zeros, so I am not worried about this voltage. I will simply put to 0. This should also be 0. So what is the point that I want to make here? Mm, okay, this is just CY. Okay, so the one thing, this is my output. So one thing is that the frequency at which we are calculating the 0. Okay, the frequency at which we are calculating the 0, CL should be sorted. Okay, so intentionally we are also trying to short the output, but we can see from this viewpoint of CL to be shorted, our output is already 0. So V out is 0 at that frequency. So one thing here. So what we are seeing here, apart from this V out to be 0, we are also making I to be 0, because it is sum of two currents. So that we are making 0 and we are getting the value of 0. Okay, so what will happen if I am increasing the frequency of the input? Okay, so when you will increase the frequency of the input, in that sense what will happen to this current and this current? Okay, so when we will increase the frequency, what do you see? Cy is near to short. There is an extra analysis I want to do here. So what will happen, this this entire current I1, this entire current I1 is going this way. Okay, so what will, when their cy is very small, the impedance offered, which I call this xy, is nearly 0, because the frequency is very high. So what I am talking about when I am saying frequency is high, much high, then cy is nearly shorted and impedance offered by the cy is nearly 0. And what will happen, the current, say okay, the current icy, or I should say icy, which is equal to vy by 1 upon cys, or which is nothing but by cys, which is directly equal to minus of I1. So our I1 is directly defined here. I1 is here minus Cys times Vy. Okay. So this is the I current. So what is happening here? This is nearly 0 amp. So here the 0 amp is copied. The entire current I1 is going this way. So your I is equal to I1 equal to 0. If I want to calculate the 0 in that high sense, high frequency sense, then what will happen here? Your Cy S into Vy equal to 0. So what exactly is happening? S equal to 0. So this 0 is coming at means origin. So is this a correct way to analyze this thing? Or simply we can say the effect of is means what I should say. Okay, the effect of this capacitance Cy is not visible at that high frequency. Okay, so instead of getting any finite value of S, which was previously coming as 2gm3y Cy, we are getting S as 0. Okay, so it is happening because we don't have two paths now. This upper path has zero current, only one path is available here, and for making the current equal to zero is not a proper way of doing this analysis. Okay, so this thing I just put here because I want to see what is the amount of current flowing through M3. Actually, the mirroring current reduces with the frequency when or Cy dominates. When the effect of Cy dominates at a higher frequency, you can see the current through the M3 reduces or it reduces to zero, so mirroring current reduces. And if the mirroring current reduces, we can see the only current coming to the output is nothing but a current going through this I1 and I2. Sorry, M1 and M2. So this thing you can see also. Okay. So this is the one analysis. Now other thing that we want to see here, what is this pole contributed to the node X? Pole contributed by node X. So pole due to node Y is very clear that what is the pole, which I call omega P3 is equal to 1 upon Rx and Cx. So Cx is the cap here. This is the Cx. So what is the Cx? Cx I can say CDD 0 plus CSS 1 plus CSS 2. Okay, the source capacitances of M1 and M2 and drain capacitance of M0. So this is the net capacitance. Now our target is to calculate Rx. This is the target. So for that, what we will do again, we will see what is the lookup impedance, what is the look down impedance. For finding the R out, we have three things here. On top of that, there is some sorted 1 upon GM3 connected. This is my M1 side. What is here toward the side of M2? This is the M2 side. Here, some sort of large impedance which I call RDS4 is connected. Okay, and this side, simple RDS3 is connected. Okay, so we see this side impedance, and this side impedance. So Rx is nothing but Rx is parallel of, let it call RS1, let it call RS2. Okay, so it will be nothing but RS1 parallel RS2 parallel RDS3. Okay, so one thing that we can see as we are looking into the sources of M1 and M2, so RDS3, not 3, it is 0. So RDS0 is nearly, means RDS0 is dominating on the sources impedances looking up in this transistors M1 and M2. Okay, so what are the sources impedance we have already seen, but we will calculate again for this. I think RS2. RS1 we nearly calculated. What was the RS1? RS1 was nearly 1 upon GM1. This thing we have calculated. Now we have to see RS2. Okay. So the same calculation way we know that let this is my M2 and this impedance I'll call it as RD for the timing, and here I want to calculate, so I'll apply a voltage source VT and this is the current IT. Okay, we want to see it. What is here? If I directly write this for ID we know that ID equal to GM VGS plus GMV VBS plus GDS VDS. So I consider my GM is dominating on GMV plus GDS. So what is the ID? ID is nothing but GM VGS. Okay, and gate is grounded. So directly what we can say here as gate is grounded. So I write here ID equal to GM. I should write 2 GM VGS 2. And what is gate? Gate is grounded. What to speak of source of 2? Source of 2 is VT. Okay. So from this point of view, what is this? This ID nothing but minus IT equal to minus GM to VT. So what we can see VT by IT is 1 upon GM2. So it is also order of 1 upon GM. Okay. So is this correct way? Because I have ignored few terms here, body effect and other things. Let if I consider these things also in my calculation. So what is the exact expression? So this is the approximate. This is the approx expression. Now I want to see the exact expression. Okay. So if you want to see the exact expression, then this is my ID. What equation we have written for the ID? ID equal to GM VGS. So what is the S minus VT plus GMB. What is VB? Body is 0. So source GDS. What is the VDS? D is nothing but drain is RD times IT minus what is the S is VT. So what we can see, it is nothing but minus IT equal to minus BT GM plus GMB plus GDS if I am considering all the effects plus GDS RD IT. So if we take the IT terms on one side and VT on other side, then what will happen? IT equal to 1 plus GDS RD equal to BT times GM plus GMB plus GDS. For the time being, I can ignore. Now I can ignore GM is greater than equal to GMB, and also I ignore GM equal to much greater than GDS. It is not this expression has to think little. It is not like that, but I am considering it. So what is the IT? IT is simply 1 plus GDS, and what is the RD? RD is nothing but RDS4. RDS4. This is 2. Okay, equal to VT GM2. So what is VT by IT is equal to 1 plus GDS2 RDS4 by GM2. Or one more thing that I can see here, you can write this as GDS2 by GDS4 divided by GM2. Okay, so if I consider one more assumption here, let GDS2 equal to GDS4, then what will happen? This impedance will look like 2 by GM2. So anyway, this impedance is not exactly 1 by GM2, rather it is some greater than that. Okay. So one conclusion here is that when some higher impedance is connected at drain, then source impedance is higher than 1 upon Gm. So this is the conclusion that I want to make here. It is coming at 2 by Gm2. Okay. So what is exactly we are seeing here? Now we can say this term is nearly 2 by Gm2, and this is of order of RDS naught. So what conclusion we are getting here? This Rx is coming as 1 upon Gm1 parallel 2 upon Gm2 parallel RDS naught. So let RDS naught is much greater than. So I can say Rx is approximately nearly 1 upon Gm1 parallel 2 upon Gm2. Okay. I consider that RDS naught is much greater than these two terms, 1 upon Gm2 and 1 upon Gm, sorry, 2 upon Gm2 and 1 upon Gm1. Okay. This usually happens. So this is the exactly impedance that we are looking in the node X, and we know the capacitance at node X is Cx. So we can calculate the pole from here. Okay. So in this video, we have seen how to calculate this zero, and how to calculate this impedances for all the nodes, like the node X. We have seen a good discussion here, and we have seen exactly how to calculate the zero. Okay, so in coming video, we'll see something else which is really interesting in terms of frequency response. And till now, I think this is enough for this video. Thank you.